Continuing on with this idea of inverses of exponential functions, that's the whole title of today's topic. We discussed this last time that if we needed to undo an exponential function, we needed some sort of function that allowed us to do that. And we discovered that the inverse of exponentials are logarithms. So we're going to spend the next two topics, this 2.10 and 2.11, kind of discussing the characteristics of these logarithmic functions before we start trying to solve equations with them. So just as we can graph previous functions, we can also graph logarithmic functions. Here's a logarithmic function. You're going to have an a value in front of the logarithm and then your base b. There's a couple of contingencies when it comes to the a and the b. The b value has to be greater than 0, meaning you will not have a negative base. The only time you'd have a negative base in an exponent is if it's a geometric sequence anyways. So you will not have a negative base when it comes to a logarithm. That base cannot be 1, because if the base was 1, 1 to any power is still 1, so it wouldn't do anything. And then the a value cannot be equal to, and that is a typo that I still forgot to fix. Wow, that's so embarrassing. This should say 0. A is not allowed to be equal to 0, because if you multiplied 0 by a logarithm, it would be 0, and the function would be constant. I literally remember making this typo last year, and I still didn't fix it. My bad. So the first idea we're going to go with today is we need to talk about what this means for us in data. You know how we've been looking at tables, and I had you tell me that linear functions change with a constant rate. Quadratic functions have a constant change in the rate of change. And exponential functions, their outputs change proportionally. You remember talking about that? Great. Let's just write that down one more again. For exponential functions over equal length input value intervals, those input values change. It says multiplicatively here. That means proportionally. You can use either word. I don't know why I don't just use multiplicatively, because I probably would spell that one more correctly more often. But this is the same as saying that it happens proportionately. Whew. It changes proportionally. This is what we learned previously. We know this. Notice how the input values are changing in equal or constant rate over equal length input value intervals. They are evenly spaced. And then we are multiplying the outputs. This is an exponential function. This is what we did in the previous part of this unit. But then last time we learned that the inverse, or 2 times ago, we learned that the inverse of a function just switches the x's and y's. And then we learned that logarithms are the inverse of exponentials. So let's say that for a logarithmic function, these two properties of the input values are reversed. So now if we look at the table, what's happening to the input values? They're multiplying. They're changing proportionally or with multiplicatively. And what are the output values doing? Adding. They're changing at a constant rate. We have switched the x's and y's since these are inverse functions. This is how you notice that you have a logarithmic function, is when the inputs are changing multiplicatively or proportionally, and the outputs are changing over equal length input value intervals. That is going to be the sentence you would have to tell me to describe to me that a table is representing a logarithmic function. So again, this might be something we want to highlight. I know it's a bunch of words. The input values are changing multiplicatively, and the output values are changing over equal length input value intervals, somehow telling me that they're equal and that this changes proportionately. Sound good? We had this down when we did exponentials, and all you have to do is reverse the language you're using, because now the inputs change proportionally and the outputs change over equal length input value intervals. So let's see if we can identify the graphs. I'm not going to have you write the sentence down over and over again, but we're going to say it. For this first table, does this represent a function that is logarithmic, exponential, or neither? Exponential, how come? And what's happening on the left side? Adding. So if we are changing over equal length input value intervals on the inputs, equal length input value intervals, and we're changing proportionally on the outputs or multiplicatively, that is an indication that this is an exponential function. What's happening on B? What do you notice? What's happening on the input values? multiplying by 3, and we're consistently multiplying by 3 every single time. What's happening on the output values? Adding 10. So if the input values are changing proportionally and the output values are changing over equal length output value intervals, what kind of function does this represent? Logarithmic. Nice. What about C? What's happening on the input values? Yeah, we're multiplying by 10. What's happening on the output values? Same thing. We're multiplying by 2. Ooh. What happens if we're multiplying on both sides? Is that logarithmic or exponential? No, it's neither. So don't just get too excited that you see the input values changing multiplicatively or proportionally. Make sure you check both, because otherwise it is not a logarithmic pattern. How about this last one? What's happening on the input values? Multiplying by 2. And what's happening on the output values? Subtracting 3. So if we have a proportional change on the inputs and a constant change on the outputs, that is logarithmic. If I were to ask you to give a reason for why you decided this table was one of these things, you would need to be able to communicate to me that the input values are changing in a certain way and the output values are changing in a certain way, just like we've done previously. Sound good? Fabulous. All right, so we're going to keep going and talk about more properties of inverses and the properties of logarithms. Some of this is going to overlap with previous lessons, so this will sound really good to us. If f of x is equal to b to the x, that is an exponential function. And g of x is equal to log base b to the log base b of x, then f and g are inverse functions. And if we compose them both directions, we should get x. This was a property we had when we learned about composition, that if we compose them inside and outside with the g on the inside first and then the f on the inside second, and both of them become x when you reduce them, that's a property of inverses. This is from our inverses notes, topic 2.8. There is one more property of logarithms that I guess I forgot to type on here that's very important. You did learn this in Algebra 2, but like I said before, I think logarithms were at the end of the school year, so we're like just hanging on for dear life. The first property of logarithms and inverses is an identity property. If you have a base b that is raised to the log base b of x power, so you have a logarithm inside of an exponential, and the bases match, I like to think of this as the bases canceling out and all that's left is x. Vice versa also works. If you have a logarithm base b and the number you are plugging into that is b to the x power, do you see how again the bases match? The base of the logarithm and the base of the exponential are both the same number, b. The bases will cancel out and we're left with x. Is a property of exponents and logarithms inverse that is going to help us do these problems. And then we need to recall just two other important properties of inverse functions from topic 2.8. Remember that the graphs of inverse functions are reflections over the diagonal line y equal to x, so a square diagonal line from corner to corner if you have a square graph. And if the point x1, y1 is on the graph of f, then the point y1, x1 must be on the graph of f inverse, meaning you switch the coordinate points, and we've nailed that down pretty well. Let's start with example 2. It says, let f of x equal to 3 to the x power, and g of x be equal to log base 3 of x. Show that f and g are inverse functions by showing that the composition in both directions ends or evaluates down, simplifies down to x. Okay, here we go. This first one wants me to put g on the inside of f. So I'm going to say here's f, and on the inside of it, I'm going to place the entire blue function g. So I have a log base 3 of x inside the f of x function. If we actually do that, the inside of an exponential means I'm putting that blue stuff up in the exponent. I have plugged in log base 3 of x to the red exponential function, pink, whatever. Do you notice that now that property I told you to remember now occurs? We have 3 raised to the log base 3 of x power. The 3's and the log are basically going to cancel out, and all I'm left with is x. That's a great start. That's one direction for us having composition work. If we compose these the other direction, where we're going to put g of x on the outside and stick f of x on the inside of it, that means that now I'm going to rewrite the g function, and anywhere there was an x, I'm going to put the red function. So it'll look something like this. So we have log base 3 of x. Well, x is going to be 3 to the x. Again, that property takes over where you have matching bases tucked inside of each other. So we have log base 3 of 3 to the x. Log base 3 of 3 cancels out. All we're left with is x. The real explanation of why this happens is coming in one of our future lessons when we start manipulating logarithmic functions. So just hang on for a better explanation of that later. To prove to you that these things are inverses and to start introducing the shape of a logarithmic graph, we're going to do example 3. It says a portion of the graph of the exponential function k of x equal to 2 to the x is shown on the graph below. Sketch a picture of k inverse, which is equal to log base 2 of x on the same coordinate grid, and then list any vertical or vertical or horizontal asymptotes. I can read. So just so we have a color coding thing happening here, that red graph printed on your paper is 2 to the x power. 2 to the 0 is 1, 2 to the 1 is 2, 2 to the 2 is 4. So we have these coordinate points here of 0, 1, 1, 2, and 2, 4. Those are known coordinate points on my exponential function. If we're trying to graph the inverse, the property we have of inverses means that what am I going to do with the x and y coordinates here? If this is 0, 1 for the red graph, what is it going to be for blue? 1, 0. We switch the x's and y's. If this coordinate point right here is 1, 2 for the logarithmic function, what is it? 2, 1. If this coordinate point right here is 2, 4 for the exponential, what is it going to be for the logarithm? 4, 2. The way that a logarithmic graph works is a bit different than a graph you've ever seen. Before we play connect the dots, because you're going to get crazy unless we do a couple extra things, we need to draw in our horizontal and vertical asymptotes. So a horizontal asymptote is going to exist for an exponential function. We did this before where we have this boundary line of y, let me make that look like an actual, y equal to 0. That's a boundary line that the exponential is never going to cross or touch. It'll get wildly close to it, especially when we're writing our limit statements to one of the infinities. Now, my question for you is, if all of these coordinate points, to get the blue ones, all we did was switch the x's and y's, what do you think we should do with this y? It's 0, so it doesn't have positive or negative. Let me ask the question one more again. Listen to how I'm asking it. If we switched the x's and y's to make these coordinate points, and this is y, what should it switch to? Make it an x, which means that our blue function is going to have a new type of boundary line called a vertical asymptote, where all we have to do is switch it from y equal to 0 to x equal to 0. You are not allowed to cross that line. You can get very, very close to it, but you're not allowed to cross it, which means when we graph this logarithm, we're going to take those blue dots and we're going to get very, very close to that vertical asymptote that we created. We go from having an exponential with a horizontal asymptote to having a logarithm with a vertical asymptote. The x and the y switches, so it pretty much makes sense. Last thing I want to show you on this graph, just so you can make sure you understand the idea of inverses. Do you notice that this line, I've already graphed it for you, but we'll draw it in with orange right now. That is the line y equal to x. Do you see how the red and the blue have like flipped over that line? That shows us visually that these are inverse functions. Again, utilizing the idea of inverse functions, we could take it a step further and bring back your favorite formula from my class. Example 4 says an exponential function h of x equal to a to the x, that's an exponential, contains the points 2, 3 and 6, 27. Find the average rate of change, ooh, yay, of k of x equal to log base a of x over the interval from 3 to 27. Question before we do anything else. What do you notice about h function and k function? They're inverses. One of them is exponential, one of them is logarithmic. They have the same base, which means that if these coordinate points 2, 3 and 6, 27 exist for the exponential, what are those coordinate points on the logarithm? Instead of 2, 3, it's going to be what?
3,
comma, 2. And then the other one is instead of 6, 27 will be 27, 6. So we have enough information to answer this question, because if I want the average rate of change of k of x from 3 to 27, don't I have an input value of 3 and an input value of 27? That's everything I need. So here's what we're going to do. We're first going to show all of our work, and we're going to say that the average rate of change is equal to, and then we're going to write the formula, which you're going to tell me. What's the formula for average rate of change? Yep, f of x sub 2 minus f of x sub 1 over x2 minus x1. But let's use the letters from this problem. Instead of f, what's the name of the function we're using? K. What's the second input value I care about?
The y. The 6.
Thank you so much for pausing. These are the x values I care about. The interval tells me the x values I care about. So what's this x2 right now? 27. And I'm going to subtract, instead of f, k of what number? 3, the first number in the interval. All of that divided by those same numbers not evaluated for k. Well, what is k of 27? What is the output when the input is 27? 6. What is the output when the input is 3? 2. What's 27 minus 3? What's 6 minus 2? What's 4 over 24? Oh,
1 over 5?
close.
No,
1 over 6. Nice. This average rate of change formula, we have to get it down pat with the correct vocabulary. So making sure that you're using the right letter for whatever problem. That's going to be important. Check done. Yes, sir. Yeah, go ahead. Topic 2.1 is just identifying for you that the logarithmic function and the exponential function are inverses of each other.